Hi folks, welcome back to Physics with Captain Rod. This is going to be video number 2 on how to use momentum to write equations for two-dimensional. But technically they're impulses because they're force times time, force times time. Now, in the previous video, I talked about how we can define our system in such a way that the net impulse is 0, and we can write a pair of momentum equations relating these momentum vectors to these momentum vectors using coordinates that were maybe this way and this way. What we're going to do here is slightly different. What we're going to do here is we're going to look very carefully at this picture, and we're going to talk about how to write equations in a different set of coordinates here. So if you give me a moment, let me draw what I'm referring to by the different set. If I draw a line right through here. Now this line that I'm drawing here, very important. This is a line that's perfectly tangent to the curve at that point. If I define that as a direction, I'm going to do this in blue. All right, I'm going to call that the tangential direction. And at a right angle to that, give or take, if I did this all right, I'm going to call, let's see, this the normal direction. Oops, let me go back there and do that again. Actually, I think I'm going to do here is shorten these up a little bit. All right, so again, I'm going to call this the normal direction. And this the tangential direction. Right, so tangential, normal. Now, one of the reasons why I shortened that vector up, let's talk vector lengths. The length of this vector represents the magnitude of the impulse during the impact. These aren't vectors, these are directions, just like an XY coordinate system, except I'm giving them a slightly different name here. This coordinate system is supposed to be tangential to the curve, this one normal to the curve. So you can think of this as a set of coordinates that we're going to use to kind of analyze this impact. Now, I'm going to also take a moment and see if I can reproduce these out here. So we've got what we're calling the tangential direction and the normal direction. Do my best to make that right angle basically. Let's see. Yeah, pretty good. Good enough. All right, so we've got tangential direction. Whoops. Go back and draw that a little better. The tangential direction and the normal direction. And we talk about why these directions are so important. If we look very carefully at, let's say, mass B here, the impulse vector acting on mass B is this way, parallel to the normal. It does not have a tangential component. And that allows us to say something very special. I can define a system as just one of these, and as long as I write an equation in the tangential direction, momentum is conserved, because the impulse on this mass does not have a tangential component. So, let me back up here, and what I'm going to do is I'm going to take this coordinate system, and I'm going to copy it. if you'll pardon me for a minute here, I'm going to pause this and be right back. Okay, I'm back there. I had to sneeze and I didn't want that on the video. So, all right. So I'm going to do is I'm going to take this set of coordinates. Oh boy. And I'm going to put it basically right here. Now, my picture could have been a little bit better because I've got this tangential vector pretty darn close to parallel to this MAVB1 vector. I'm not going to change. I'm just going to move on to the video. It's going to be fine. But what you need to realize is that in general, there is going to be a small angle right here. All right, I'm going to give that vector a name. I don't know, maybe theta. All right, now I'm going to go ahead and copy that again. Put another one over here. And you'll notice over here, there is an angle between this vector and the tangential direction. I'm going to give that a name. Oops, I put that in a better place. All right, maybe something like this. I'm going to call that, let's see, theta, beta, I guess. All right. Now I'm going to put another coordinate system here. And again, you'll notice there's an angle between the tangential direction and the normal direction. Call that one phi, and I'm going to go ahead and put, actually let me make another one there, okay, put that one here, right, and then here's an angle right there. I'm going to call that one alpha, right? So what we're doing now is we're going to write equations in a completely different set of coordinates. We're going to write equations that are in the tangential direction and the normal direction. And the tangential one is the one that we want to start with, because we know that there is no impulse, looking at this picture, in the tangential direction on either of these two masses. So I'm going to take this and just store it off to the side in case I need another one of those. Now, I can actually write quite a few equations here. So what I'm going to do is define my system like this. Just mass B. And we can actually write a conservation of momentum for mass B only in the tangential direction, calling kind of up and right here the positive tangential direction. In order to do that, however, I need the component of that momentum vector in the tangential direction. Now, I know that looks like they're parallel, but they're not perfectly parallel. There's an angle theta. The magnitude of that vector is MBVB1. If I multiply that by cosine theta, I would get the component in the tangential direction. So what we're going to have here is MBVB1 cosine theta. I don't have a second term like the previous video because of how I'm defining my system. I'm writing an equation only for mass B. Now, you might be asking, why did he pick mass B? Why not mass A? I just flipped a coin. You can do either one. I'll go ahead and talk about writing the equations for mass A here in a moment. So, MBVB1 cosine theta. That vector would be positive because that component is up and right in the tangential direction. Only one term because how I'm defining my system as only this mass. I look here, and again, there's no impulse. This impulse does not have a tangential component. Then I look over here and I say, well, here's my MBVB2. The component that is in the tangential direction I get by multiplying by cosine beta. Let me just real quick in red make sure that I'm going to draw these components so everybody can see what I'm talking about. The component of that vector in the tangential direction would be maybe something like this. This would be the component of this vector in the normal direction. Now you'll notice this one right here is adjacent to beta. This one is opposite beta. So I'm going to use that fact when I write these equations. All right, so MBVB2 cosine beta. And these we can say are equal because this impulse does not have a component in the tangential direction. Now, in a lot of these problems, if we knew any of this stuff, maybe the thetas and the betas, we can relate VB2 to VB1 quite easily. By the way, you'll notice the mass divides out of that, but I'm not even going to bother doing it. We can also write a conservation of momentum for mass A in the tangential direction. And again, same tangential direction. So I look at mass A. Here's its momentum vector. There's an angle phi with what I'm calling the tangential direction. So that's going to be MA VA1 cosine phi equals. So hopefully now, if you've been watching the video, you'll know what that right-hand term is. All right, so this black vector is MA VA2. It's the momentum vector, picture 2 for mass A. Here's the tangential direction. Here's an angle alpha. It's that small angle between the tangential direction and that momentum vector. All we have to do is multiply that by, let's see, cosine MA VA2. We want to multiply that by cosine alpha. And that would give us the component of the black vector in this direction. And again, we can put equality between these because this impulse does not have a tangential component. So what we have now is we have a pair of momentum equations now that we've written. And if you look back to the previous example, you'll notice that we were able to write two momentum equations for the x and y direction. Well, one for the x, one for the y. Here, looking at these individually now, we were able to write two more equations, one for each mass in the tangential direction. Now, you might wonder, can we write equations for the normal direction? And the answer is yes. We can write equations for the normal direction as well. However, the normal direction, right, this is an impact. So the normal direction is, for lack of a better way to put it, governed by what's called, the coefficient of restitution. So hopefully you've watched my video about coefficient of restitution. Just a quick little reminder. The coefficient of restitution is defined as the ratio of the restoring impulse, I guess I would call it, the integral r dt, over the deforming impulse, integral p dt. All right, so again, you'd want to go back to a previous video to review what that is, but an important thing here is that the coefficient of restitution, by the time you work out all the math, if I have a VB and a VA, it's equal to VB2 minus VA2 over VB1 minus VA1. I'm going to take a moment here. I got to take a quick little break here and pause this. All right, folks, I'm back. Sorry about that. All right, so let me just kind of recap what we've been doing here. So we've talked about how to write equations in the tangential direction for both of these masses individually. That allowed us to write two more equations here, MB/VB1 cosine theta equals MB/VB2 cosine beta, and the following for mass A here. Now we're talking about how to write an equation, a conservation equation in the normal direction. Now, we don't want to define them individually now for the normal direction because we don't really know about what this impulse is or this impulse. But what we can do is apply coefficient of restitution, which is coming from momentum conservation, along the normal direction. And the coefficient of restitution is equal to VB2 minus VA2 over VB1 minus VA1. It's important to realize, though, that this, pardon me, this applies only normal direction. So like this VB2 is not the magnitude of this vector. It would be the n component of it. So when we write this out, we're going to have coefficient of restitution equals. All right. Now when you apply this, another thing is we have to talk about which way we're calling positive. I've got the positive normal direction up and left. So I'm going to take note of that here, that we've got up and left positive. VB2 in the normal direction, I look here now, VB2 makes an angle beta with the tangential direction. So VB2 cosine beta gives the tangential component. VB2 sine beta gives the normal component, and that component is pointing in the opposite direction of what I've got as positive here. So this term is going to be minus VB2 sine beta. Right? The sine beta is, again, because this coefficient of restitution applies in the normal direction here. If you go back and look at the video of deriving this thing. The minus is because I've called up and left positive, and this y component is down and right. So there's that term, right? Minus VA2. So we're going to have minus. Now, this is VA2. VA2 cosine alpha gives me the tangential component. VA2 sine alpha would give me the normal component. And hopefully you can see this. The tangential component would be this way and would be positive, but the normal component is kind of down and right where I've got up and left positive. So we're going to have minus a minus VA2 sine alpha over, right, VB1 minus VA1. So I look over here. Let's see, B. So here's VB1. It makes an angle theta here with the tangential direction. So VB1 cosine theta would give me the tangential component. VB1 sine theta would give me the normal component, and hopefully you can see from my picture the tangential component is kind of like up and right, the normal component is up and left, and that's in the positive end direction. So we're going to have VB1 sine theta. That term would be positive because I've got up and left positive, and the component of that black vector in the end direction is positive. Right? Then minus VA1. So I'm going to look at my VA1. Now, it's hard to see here, but MA VA1. VA1 makes an angle phi here with the tangential direction. VA1 cosine phi would give me the tangential component of VA1. VA1 sine phi would be like this, opposite direction of the normal. So let's see, that's going to be minus a minus VA1 sine phi. Right? Now I'm not going to bother cleaning up anymore. What we would then do is go through and, this would be plus, this would be plus, and so forth. So if you look at what we've done, we were able to, by looking at the tangential and normal directions, basically based on this picture, we're able to write 3 more equations for this problem. We can write a momentum conservation in the tangential direction for each mass individually, allowing for 2 more. And again, the key to that, to understand why can we do that, because the impulse during the impact between these lines on this axis does not have a tangential component. So because it doesn't have a tangential component, the tangential components of these momentum vectors do not change. So that's what allows these. Right? Looking at the normal direction, right, these impulses are changing the momentum of these individually, and that's what that coefficient of restitution is all about. So basically we're applying the momentum conservation along this normal, taking into account the coefficient of restitution. And that's what allows us to write this final equation here, writing 3 more. So I'm going to go ahead and call that video done for now. I hope it demonstrated how to use tangential and normal directions to write equations for momentum or for impacts. And I'm going to go ahead and work on some examples. Have a great day.